All right, so I know we got at least one, well, up at the most 1 minute before 5:30, but I'm going to get started a little bit early, just because this part does not really relate to the class content. Some of you probably, if you subscribe to the channel, you probably got notified of Tech's take on software engineering / developer as a career path. Okay, so it's not intended for you guys. Okay, it's intended for our counselors. At ARC, so that they kind of more understand, they understand more about software engineering, what it is about, what is the job outlook, what is the median salary, how is it different from being a programmer, okay? What type of education background is needed, and so on and so forth. And if people are interested, what can they do? They can, sign up for our classes here. Get their computer science degree out of here, transfer to a 4-year university. In other words, stuff that you know already, because otherwise you wouldn't be here, right? So that's why I'm not going to show the whole thing. But what I do want to talk about a little bit here, if you watch this thing, there's a little bit about Mbti. I think I talked about Mbti or Myers-Briggs type indicator a little bit. So when you look at the distribution of Mbti types within the software engineering population and compare that to the general population, it's very different. Certain types are overrepresented by 400+%, and other types are underrepresented by, like, they're basically 1/8 or less of what their normal natural population is. So it's kind of interesting because if the sample size is not that big, but yet it does show certain trends. So it's interesting from that perspective. I'm not saying certain types are not suitable for computer science or as computer engineers, but there is a correlation somewhere. Okay, there's a skew somewhere. What is also interesting is in that table, the type INFP, 0%. No INFP within the sample of software engineers. So no software engineer that they studied was an INFP. Okay? Now, the difference between an INTP and an INFP is really kind of a fuzzy line. Okay? So I sometimes cross over that line, and sometimes I can be tested sort of as an INFP. So take it totally with a grain of salt, okay? So that's kind of interesting and definitely optional for you guys to watch because most of you know that stuff already, okay? But it does have some resources that you might want to kind of look into. For instance, if you go to the website called hired.com, HIRED.com, they will give you pathways to different types of software engineers. So if you say, I want to be a machine learning engineer, there's a specific pathway to that. If you say, I want to be a full stack engineer, there's a specific pathway to that. If you want to say, I want to be a VR engineer, okay, there's a specific pathway for that. So, so hired.com is an interesting resource that you might find useful, okay? It may be a little bit early for you guys to look into that because you still need to get your bachelor's degree first before you specialize and try to get into a specific kind of engineer. But it doesn't hurt to kind of keep an eye out for, oh, okay, so what type of engineers are out there and how do I become one of those, okay? So that's one. I just came from the Design Hub, and the Design Hub is in need of developers over the summer. So if you want to learn, you don't have to know it already. If you want to learn about Unity programming, if you want to learn about VR programming, or if you just want to play with VR gear and you decide, I don't want to spend my own money on VR gear just yet, okay? We got vacancies, okay? I don't know whether it's going to be paid or not, okay? But paid or not, you will get access to our $10,000, big boy desktop computer, that can do all kinds of smooth, rendering in VR. We have some pretty nice gear in terms of VR stuff, not super top of the line, but we have the I think it's called a Vive, right? the HTC Vive. So we got one that has the wireless kit. So with a battery pack, it's totally wireless. You can actually just turn around, all day long. And well, if you don't, you won't get tangled, okay? Whether you get dizzy and fall down, that's a different story, okay? They got the pugs, okay? So they got the pugs, which are encoders, so you can actually attach a pug to, let's say, a pipe, okay? And then you can program, the Unity program to track the motion of the pug. So you can now swing a bat and have the VR program to track, the bat in VR. So it would actually show the bat in VR as if you're holding it. And according to Professor Schuster, it's actually pretty realistic in the VR environment. So we got all of that toys, okay? If any one of you want to learn about VR programming or how to do it in Unity and stuff like that, we are definitely interested. So let me know, okay, or let Professor Schuster know about it. I don't know the details yet, okay, because he just talked to me like 20 minutes ago and say, Tech, we need a lot of VR people in the design hub, okay? So I'm just relaying the message. Just in case some of you are planning, well, between that and the trip to Europe, it's hard to, it's a toss-up, right? But, but we do have stuff going on at the design hub. So that is that. And then the third thing, okay, you guys probably got my email about I have to move my office hour and cancel some and blah, blah, blah. That's because I'm in a residency with IBM, okay? A residency means, I'm just, getting together with other SMEs, okay? IBM loves abbreviations. Does that surprise you? There you go. So IBM loves abbreviations. So SME stands for Subject Matter Experts, okay? It's not really that difficult to pronounce, but yet everything has an abbreviation, okay? So I'm just getting together with a bunch of SMEs, about 3 or 4 from IBM itself, 2 from the California state government, and myself, from ARC. So the purpose of this residency, which is supposed to last 4 weeks, the first 2 weeks are supposed to be full face-to-face, so they want me to be over there from 9 to 5, Monday through Friday. And I said, no, I don't think I can do that. But it's interesting, because the whole purpose of that residency is to establish, okay, the mic is on, that's good. So the whole purpose of the residency is to help IBM to use public money, okay, tax money basically, to come up with a mainframe COBOL programming course that is freely accessible to everybody. So IBM doesn't get to put its brand on the product because it's made using money that taxpayers put into. So it will be available to, I think, at least Coursera, and I can use it in my courses as well. Okay, so this is all about programming mainframe computers using JCL and COBOL and stuff like that. How many people have even heard of JCL or Job Control Language? Okay, ask if you have a grand uncle, or grand aunt or grandparent, okay, who used to be in the IT field, ask that person, okay? That person may be able to tell you something, okay? Your parents will not be able to tell you anything, okay? It's kind of, it came from the 60s to the 70s, okay? So those many programs, that are still in use by the Franchise Tax Board, the EDD, or the EDD stands for what? Employment Development and, is it Employment Development Department? Okay, so it's a pretty big branch of the state government. The DMV, okay, you guys all know about the DMV, right? So the DMV, how about Wells Fargo? Do you know about Wells Fargo? The Wells Fargo Bank, American Express. All of these big, huge institutions and corporations, guess what? They're still running programs that are written in COBOL. Okay? So what is the problem? The problem is their employees are disappearing. They go like, well, if they retire, they can always hire them back as consultants. No, They are dead. They're dying, okay? My late uncle, okay, my own late uncle, I can tell you this kind of funny story. I know it's not totally related to this class. My late uncle, who passed away about 10 years ago, when I first came to the United States in 1985, my uncle told me and say, Tech, you got to learn JCL. This is really useful stuff. And he was a programmer for the City Hall of San Francisco. So he works for local government, not even a state or federal government. And he said, oh, JCL is really useful. Okay, go ahead and learn COBOL. This is useful stuff. And I kind of look at it and go like, no, I don't want to learn that, right? Well, sure enough, many, many years, many decades later, it comes back, okay? Because the state, IBM, and all its clients are now saying, we need people, and there's no one, okay? Now, if a company is to have a job posting and say, okay, we need people who can program in Java, okay? You get tons of applications. You get to choose, right? If they say, I need someone who can program in C# or JavaScript, okay, or Python, you get tons and tons and tons of resumes. And then the moment you ask, we need people who can program in JCL and COBOL, nothing, okay? And yet, those are important jobs, okay? Because the state government needs to keep running. And you ask, well, why can't they just keep the old programs, just operate the way they are? Because they have to incorporate new legislatures into the programs. If they change the tax law, then those programs have to reflect the changes. Does it make sense? So they have to do maintenance on those programs, and yet the number of people who can do that kind of job is decreasing. And the state knew this way ahead of time. It's just that they don't have a mechanism to increase the pool of people who can take on those jobs. And what about Davis, UC Davis? What about Sac State? Why don't they teach COBOL or JCL? What do you think? No
professors that teach it, or is it a small pool?
No professors want to even touch that stuff because it's not academic. Okay? It's not academic, and most professors do not know that stuff, nor do they want to learn about that stuff. The last time I programmed in COBOL was when I was about to graduate from high school. And that was a long time ago. Okay? So that's the kind of stuff that we are dealing with. But for those of you who want to look into a specialization of different types of programming in terms of I want to be able to land a job, okay, where there's not a lot of competition. This is one of those areas, okay? So I just want to throw it out there for you guys to start thinking, okay, about all of this stuff here. All right, so that's all the background stuff that I want to share with you before we continue with our discussion. So. And by the way, Visual Studio is now natively installable on Linux. So it's kind of cool. Huh? All right, well, let me show you what I mean by that. So, yeah, VS Code. And yeah, but there are tons of extensions, and most of these extensions I can get it to work. So I was, when I was at IBM today, we set this up so that we can actually sign on to a mainframe computer and then investigate or explore the data sets and whatnot. So, and it also has a COBOL editor, so it's syntax aware. Yep, it's all pretty cool stuff.
Some friends of mine recommended that software.
Oh. Yep. So things are, kind of interesting. So just want to share with you what I did today, which is not entirely related to this class, but some of you may find it, informative.
So how did you find COBOL programmers now?
Sorry?
Where did you find COBOL programmers? Is it just people that are self-taught?
Well, the first thing they do is they try to cannibalize each other. And it's not even just the state. Bel Air, okay, the supermarket chain, Rayleigh, Bel Air, Wells Fargo Bank, the state, the city of Roseville, they all cannibalize each other. Because the local pool of people who can actually work with mainframes and program in COBOL is a very small pool. So there's a big demand of people like that. Yep.
So are COBOL programmers getting paid a lot more?
Nope, not in the state. Okay, so in the state, it all depends on your classification. So within the classification, there's a certain range of salary. So they don't get paid any more than other people of the same classification. The question is, how difficult is it to get a job within that classification? So if you try to get into a job of that classification that does, say, Java programming, competition can be stiff. Okay? On the other hand, if you have another job opening of the same classification and the job requirement is JCL and COBOL, you may not encounter nearly as stiff, of a competition. So that is the difference. Is how easy is it for you to get into a job like that? The state is interesting because once you get into a job, you can transition within the state government, and there are tons and tons of variations of the same classification within the state. So there is the really cool part of working for the state is it's a huge employer, and you maintain your retirement plan the whole time. So it's not like you quit a job and now your retirement plan is no longer the same, or it just continues. It doesn't count your years anymore. It's the same employer. So did I answer the question? Okay, cool. All right. So we are getting back to our stuff here, and we are about to talk about, we are still on this slide, which is D flip-flops and basic memory devices. So we'll go ahead and dig into this. All right. So last time we talked about the SR latch, which is a kind of weird memory device, okay? Because it doesn't really quite, quote unquote, remember something. It has two levers, okay? One lever says, I want you to remember a 1 now, okay? And the output state is a 1, okay? And then the other lever says, I want you to change the state to a 0, and now it remembers a 0, okay? And that's kind of a weird memory device because you have to tell it, I want you to remember a 1 or a 0, okay? So that's kind of awkward from our perspective. Okay, and this is the stuff that we went over before the test. So now we move on to, so what you're seeing right here, is the analysis of the device, which we did in real time, during the lecture last time. So I'm not going to repeat all this stuff, and instead, what we'll do today is we'll start with a D flip-flop. So a D flip-flop, okay, is a memory device that is built on top of an SR latch. So if you do not know what a SR latch is, it's kind of difficult to understand a D flip-flop. But in this one, unlike a SR latch, a D flip-flop has a data bit which says, this is what I want you to remember. And then it has a separate bit which is called enabled or clock, it depends on the terminology, that says, okay, now go ahead and remember it, okay? So what we want to do is to look at the text representation, which is down here, and then use it to implement a D flip-flop. So are we good so far? Okay. The first thing we need to do, that I need to do, is to start Java and start the program. So we'll go ahead and start Logisim. Go. And I actually kept the program that the circuitry that I built last time. So this is a D flip-flop. I'm not going to explain the D flip-flop today because that's what we did last time. But what I'll do today is to turn that into our circuit so that we can use it in a D flip-flop, okay? Huh? Oh, that's an SR latch, and we're going to use it to make a D flip-flop. Thank you. So we'll change the name, okay, from main to SR latch. And I need to change my glasses because I cannot see a single thing with this one. There we go. All right, so this is a SR latch, and then we'll change the appearance so that I can remember which pin is which pin. I pretty much know which one is which one, but from your perspective, I want you guys to see which one is which one. So this is a /s or exclamation S, okay? Either one is fine, depending on your notation. So the slash or the exclamation point is a negation. It's a Boolean negation. So what that means is when the signal of that pin is low, we want to accomplish what the label says. Okay, so in this case, when the signal is low, we want to set the output pin, which we call Q. This is the negation of Q, so it is just not Q. And over here, we have not S, not R, excuse me. So that's for resetting. So we have one pin for setting, one pin for resetting, and then two output pins. One is the non-negated output, and the other one is the negated output. Yep.
Not S and R. It wasn't not. I thought it wasn't not R. I thought it was just R.
No, it's the negation of that. It's also active low. They're both active low. The circuitry is interesting in the sense that it is a mirror image, top down. So if you were to draw a line through the middle horizontally, it's symmetric, on those two sides. So they're both active low. All right, so we are done labeling the pins. There we go. And then we can now work on something else. So we go to project, add another circuit, and this time it is our D flip-flop. So I just use DFF or D flip-flop. And then we need to look at the documentation and find out how to build a D flip-flop. So the first thing we need to do is to find out what components do we need. So we need a NOT gate here. We need two NAND gates or NAND 2 gates. We need one SR latch, two input pins, and two output pins. So this is kind of the recipe, okay, in terms of the ingredients. These are the ingredients of your recipe. So we'll go ahead and fetch all of those parts. So what I'll do is I'm going to put this one out here. You cannot see it, but I can see it. This is how I can get the right components in. So we'll go ahead and fetch a negation, a NOT gate. We'll go get two NAND gates. So we go to NAND. And we have to change the configuration just a little bit. There we go. And we need two of these. We need an SR latch. So I just built my own SR latch earlier. So this is my SR latch. We need two input pins and then two output pins. So here's one, here's another one, and this is my first output pin, and this is my second output pin. Okay, so now we got all the ingredients. It's good to name these things first. So this is my N, which is just a negation NOT gate. This is my N1. I'm just reading off of my own description on the side that you cannot see. This is my SR latch, which is just called SR itself. And this is my output pin Q. And this is not Q right here. And then we have two input pins labeled D and EN. So one is D for data, and the other one is EN for enable. Okay, enable means it's time to remember something. Okay, all right. So now that we got this part done, okay, we can kind of drag this part back in, so we can see how to make all the connections. So we'll start with the D pin. The D pin needs to connect to the first input of the N1 NAND gate and also the negation input of the NOT gate. Okay, so we'll go ahead and do that. So switch back to here. So it needs to connect to this one and also the first input of N1. So here's one connection, and here's the second connection. This is one node. And then the second node connects the EN pin to the second input of N1 and the first input of the second NAND gate. Okay, so here's the second NAND gate. So let's see. I think it connects to the second input of the first, and then the first input of the second one, like so. Double check. Yep. Okay. Then we connect the output of the NOT gate to the second input of the second NAND gate. So we take this output and we connect it to the second input of the second NAND gate. And then we take the output of N1 and hook it up to SR.S. Okay. So we take the output of N1, hook it up to S, and then we take the second NAND gate's output and hook it up to R of the SR latch. Oh, I did not quite finish that connection. There we go. All right. And then we have the R of the SR latch connecting to the R output pin and the NQ to NQ. Okay, so that's fairly easy. Okay, to make it look nicer, I can align things like so. Put it one over here and put the other one over here. Okay. Then you guys go like, hey, what's the error? Well, the error has to do with the SR latch has no known previous state. So you cannot ask it, what is your current state? Nobody told me what state I'm supposed to be in. Because when both inputs are ones to a SR latch, we are neither setting nor resetting. We're simply saying, just maintain your current state. But I never told it what the current state really should be, so we kind of need to change it first. So the moment I enable this enable pin here, it's going to mirror the state of the D pin to become the output of the SR latch. So right now it's going to remember 0 as R, as SQ. So you can see how that works. Okay. So the thing about this particular D flip-flop is the enable pin is known to be what we call level sensitive. In other words, whenever the EN pin is a 1, whatever the D pin is experiencing, the Q pin will follow. So as long as I keep EN to be a 1, I can go to the D pin and change its state, and you can see how the entire thing just mirrors. Okay, it will copy the state of the D pin to the Q pin as long as EN is a 1. Okay, it will stop doing it if I turn the enable pin from a 1 back to a 0. Then it does not do anything anymore. Okay, it does not update the output based on the D pin. So we're still doing okay so far with this particular circuitry. So in terms of behavior, this is kind of what we are expecting as a memory device. Okay, here's a bit, and now we say, go ahead and remember it. Once it is remembered, we will turn it off. We'll turn off enable and to maintain the state of that one bit. So are we doing okay so far with the mechanism of this circuitry? All right. But how does it work? Okay, so we want to understand how it works. So to understand that, I'm going to turn off simulation first and reset everything so that we don't have those lines in light green and dark green to interfere with our interpretation. Okay, so the first thing we want to do is, what is the enable pin doing? How come the enable pin has this magic of enabling or disabling the SR latch? So let's track down what EN is going. EN is going to both N1 and N2 non-negated. Okay? So when EN is a 0, what do you think is going to be the output of N1 and N2? Or does it not, or can we not determine that because we also need to look at the other pin? What do you guys think? It's going to be a 1. Okay? So whenever EN is a 0, both N1 and N2 are guaranteed to output 1 because both of those are NAND gates. When you have a NAND gate, if at least one input is a 0, the output is guaranteed a 1. Are we good so far? But what are those outputs going to? What is N1 and N2 feeding into? the S and the R pins of the SR latch. So from the previous lecture on SR latch, what happens when both inputs of an SR latch are ones? Maintain the current output, okay? No change, just maintain the current output. So that's why enable works. Now, what happens when the enable pin is a 1, okay? So that means one input of N2 is now guaranteed a 1, and then one input of N1 is also guaranteed to be a 1. But because N1 and N2 are NAND gates, having just one input guaranteed to be a 1 doesn't guarantee the output at all. So now the output depends on the data pin. Does that make sense? So when you look at the data pin, okay, this is the best thing about being able to track this down. The data pin goes to N1 non-negated, which means if the data pin is a 0, then N1 is going to guarantee to output a 1 to not S, which means don't set, right? What about N2? N2 gets D, but through a negation, through a Boolean negation. So that means whenever the D pin is a 0, N2 is going to get its input as a 1. Is that okay? When N2 has both inputs being 1s, then its output is going to be a 0. That 0 is going into not R of the SR latch, which then resets the output of the SR latch to a 0. Is that okay? So this circuit is actually quite a bit simpler to analyze compared to SR latch itself because there's no feedback. Everything just keeps going forward. Are we good so far? So this is a, go ahead.
This kind of feedback is there because an SR latch has feedback in it.
Say that?
The SR latch has feedback in it, so there is
Correct.
to some extent feedback.
So the SR latch is slightly more difficult to analyze because of the kind of cross-path feedback. But this one does not, so it's a little bit easier to analyze, assuming that we know what an SR latch is.
I'm just kind of confused how you're saying that this circuit doesn't have feedback as it contains an SR latch that does.
It does if you look into what an SR latch has, but if you look at the SR latch as a black box, then the D flip-flop does not have a feedback. So assuming that we know the behavior of an SR latch, this circuit is now easier to analyze. Yep. So are we good so far with a D flip-flop that has a level sensitive enable? Okay, very good. So moving on to the notes. Okay, so this is a D flip-flop and the explanation. So the next one is a little bit more difficult because this is a what we call an edge sensitive D flip-flop. Okay. So we'll go ahead and construct it first, okay? So once again, I'm gonna pull this to the side so I can read it, but you guys can see how it is constructed. Go to project, add circuit. This is a edge sensitive D flip-flop, okay? We need 2 SR latches this time. So we go to SR latch and then we pull 2 of these things. The first one is called S. The second one is C. And then we need 2 NAND gates. Now this time the NAND gates are a little bit weird because the first one has 2 inputs, the second one has 3 inputs. So we look at the first one, it has got 2 inputs. And we'll call it N2. And then the second one, which I can duplicate from this one, has 3 inputs. And we'll call this N1. All right, we got 2 input pins. One is clock, CLK. And the other one is data, which we can just abbreviate as D again. And then we only got 1 output pin this time. Only Q is important to us. So we only got 1 output pin, which is Q. There we go. So these are the components of the edge-sensitive D flip-flop. Okay, so let me pull the other screen a little bit closer here so that we can see what we have done so far. So what we have done so far is to look at the recipe and collected all the ingredients. So the next thing we need to do is to follow the recipe and make connections between the ingredients. The data pin or the data input pin connects to the second input of N2. Okay? So the tricky part of doing this is to make it look nice. Okay, because if I'm not careful, we can end up with something that looks really ugly. And I can still remember how to order things, because the name of the devices kind of implies which one is on top and which one is at the bottom, like that. Between S and C, I cannot remember. And this is the output. We can rearrange things a little bit differently later. So we connect D to the second input of N2. All right, so this goes to here, okay? And then we connect the clock pin, which is this guy here, to S.R directly. So that goes straight to S.R and also the second input of N1. So it goes, oh, this is ugly. There we go. And it also goes to the R pin of SR latch S. All right, then we take N2, output of N2, and hook it up to N1's third input. So we take this one. Okay, for those of you who are artistic, you are more than welcome to create your own circuit that looks nice. Okay, and it also hooks up to S.S. So S.S is up here. Okay. So let me show you what I have done so far. So, oops. So at this point, we have done this part here. So now we're going to take the output of N1 and hook it up to the first input of N2 and also C.R as the input. All right. So we take N1's output and hook it up to the first input of N2. Okay, is there a nice way to do this? We could do tunnels, or we could do this. No, I did not say that I wanted to look nice. I said for those of you who wanted to look nice, you can go ahead and make it look nice. All right, so it also has to hook up to C.R. So we take this one and hook it up to C.R. So we can move this one so it aligns a little bit better. There we go. The next one says you hook up S.NQ. S.NQ is right here to N1's first input. Okay. It's okay, we got it, I got it. And it also has to go to C.S. So this is the other one that has to connect to. Oh, see, nice and handy right there. Okay, so we got that. Okay, and the last one is C.Q, which is this one. Has to hook up to the Q pin. Okay, that's the easy one. Okay, I must be forgetting something here. Because what about S.Q? S.Q is not used. And do we have any input pins? Okay, so how do you check the circuit is good? Yep, go ahead.
Would the Q or S.Q hook up to the non-existent NQ?
No, they do not. So you don't, okay, so how do we know? Okay, so how do we do a sanity check? Even though you have no idea what the circuit is supposed to look like, how do we know whether it is okay now or not? You look for input pins that are unconnected. Okay, if we have any input pin that is unconnected, something is wrong. Okay, so we'll double check. N1 has got all three inputs connected to, that's good. N2 got both inputs connected to. SR latch S has got both inputs connected to. SR latch C also has both inputs connected to. So that's the first sanity check. Okay. Now, what about the output pins? Okay, you can see that the Q output of S is not connected, and then the C.Q is also, no, C.NQ is not connected. It's okay for some circuitry to not to have the output connected simply because we really don't have a use for that. Okay, so I think we're good. Okay, because the sanity checks basically says, okay, we got all the input pins connected to and stuff like that. Okay, so it's time to check it out. It's time to run it and see whether it works or not. So we'll enable simulation. Okay, and the output of this is undetermined or is an error once again because we just turn on the device, right? And both inputs of the SR latch, in this case SR latch C, are ones. So we are basically just telling the SR latch, maintain your current state. But we never specified what the original state was, and then we just power up the whole device. Okay, so that's why it's a red line, which means the simulator cannot determine what that state is supposed to be. Okay, all right. So that means we have to somehow make it remember something. So it's up to you guys. Do you want it to remember a 1 or a 0? It's up to you. A 1? Okay. So if you wanted to remember a 1, then you have to change the state of the D pin first and say, okay, I want it to remember a 1. And you can see how changing the D pin doesn't do a single thing to the output state. Okay? Although it does change a few things, it doesn't change the output state of the CSR latch. So the magical quality of a clocked D flip-flop or a edge-sensitive D flip-flop, they mean the same thing, is it only copies the state of the D pin to the Q pin overall when you have a rising edge at the clock. Only at the moment that the clock is transitioning from 0 to 1, it will copy the state of the D pin to the Q pin. Question? Nope? Oh, okay. Yeah, go ahead.
So that's why you have to do the D pin first, or before you want it to be.
Correct. Yep. Whereas the other one, says as long as the EN pin is a 1, you can keep changing the input pin D, and the Q pin as the output will follow. Right? This one doesn't quite do that. This one says only at the moment that the clock pin goes from 0 to 1, it will remember the D pin. Okay? So this is the magical moment. Okay? If I make a mistake, it's probably not going to work. Ting! Ah. Then you go like, well, but we don't really know whether this will continue to change as long as the clock pin is a 1. If I flip D around, would it change the state? Okay, so let's check it out. It does not. So it's kind of interesting, right? Okay, so how do we change the output to a 0? You have to change the D pin to a 0, and then have another transition, 0 to 1 transition of the clock, then the output pin changes. Yeah. So this is edge sensitive instead of level sensitive. Okay? Sorry? How does it work? Well, I cannot remember either. But that's why I wrote this. All of this explains that. So, how do we read all this stuff? Okay, as the section heading tells you, this is the analysis of what happens when the data pin is a 0 and we see a rising edge of the clock pin. Okay, that's basically what this subsection is about. So now we start with, because in order to have a rising edge, the pin has to start from 0. Okay, so the first state of this entire event is the clock pin starts with a 0, the data pin is a 0. And you can see I'm using double equal here because I'm not changing the pin's state. I'm only stating that it is now a 0. Okay? All right. So when this is happening, S.R is a 0 because of the way we hook up the pins to SR latch S. And as a result, it causes S.NQ, which is the same as C.S, to be a 1. So let's go back to the circuitry, okay, and see what happens. Okay, so what we do is we turn off simulation so that we don't get distracted by the light green and the dark green wires. And we say, okay, both of these are 0s, okay? What do they immediately do? Well, if they're both 0s, they will change N1 and N2 so that the output of N1 is going to be a 1, and then the output of N2 is automatically going to be a 1 as well. Okay? But what is that going to do? Okay, we follow those wires. So this is a 1, okay? And we also know that this is a 1 as well. So ones don't do a single thing, they don't change anything. And that's basically, it causes s.nq to be c.s to be a 1. This part I know for sure, but I think this one is, s.r is a 0. s.r, why would that be a 0? Oh, because clock is a 0. Okay, because it connects directly to it. So because clock connects directly to SR latch S, and this is now a 0, and the other one is a 1, because we know N2 outputs a 1. So that means we are resetting the output of SR latch S, which also means SR latch S, the output Q is going to be a 1, excuse me, a 0, but the NQ is going to be a 1. That's what it was saying. Is that okay so far? No? Maybe? Okay. So this is where it's going to be helpful for you guys to print several copies of the same circuitry. And you just label all of these wires, starting with the things that you know, and then you start with things that you can say, well, if I know this is the input of this thing, I know the output of that thing is going to be blah, blah, blah. Is that okay? Do you guys want me to kind of go through this once?
Please, yes.
Okay. So it's the technique of doing this more so than really the documentation. The documentation in the notes explains this already, but I want to show you how you can do it yourself. So let me export the image first. As a PNG is fine. Okay. And we'll put it into /temp/edge sensitive D flip-flop.png. And now we can go to Zerno. Okay, move this up here. And then we can insert a bitmap. There we go. And we'll put here. Edge sensitive D flip-flop. There we go. All right. So we stash it. Oops. All right. So once we stash it here, we can now document it. Okay. All right. So we'll do this step by step. Okay. And I'm going to use a color that is kind of more visible. Let me know whether this is okay with you or not. Can you guys see this is green? Yes? Okay. So we start with those 2 pins, and I can zoom in just a little bit so that we can. There we go. I think this works a little bit better. Okay. So this is all we know initially. Okay. So the next question is, knowing that D and clock have zeros, what else do we know right away? Okay. Well, we know this is going to be a 1, and we know this is going to be a 1. Is that okay? Because one of the inputs of N2 is D, and one of the inputs of N1 is clock. And both of those are NAND gates, which means if at least one input is a 0, both NAND gates would output 1s. Is that okay? But the other thing that we also know is clock, okay, following the clock pin, it goes straight to here. So that 0 also goes all the way here. But that is, okay, so the other thing we also know is this is a 1, but this 1 goes all the way here as well. So that means we know from the perspective of SR latch S, it is seeing not S or N, not S as 1 and not R as 0. And because the inputs are what we call active low, so that means the one that has a 0 specifies the action that we want to perform. And now we want to reset, right? So this 0 over here is the output of the Q pin of SR latch S, which doesn't go anywhere. So it might say, hey, this is useless. We don't need it. But wait, but that would also simultaneously change NQ of the same SR latch. So that means the not Q of this SR latch is now going to be a 1. Where is that one going? Well, that one goes here. Okay? So now we know one input, or not S as the input of SR latch C is going to be a 1. What about the other one? Well, the other one is known to be a 1 too, because that one is the output of N1. So now we have determined the inputs of everything, or at least to the point that things are determined. Is that okay? I don't need to know, the other pins to N1 or N2, because if at least one input is a 0, why would I care about the other input pins of the NAND gates? I already know the output already. Is that okay? So this is how we analyze the circuit in a static way and just say that, okay, what happens when both inputs are zeros? Okay? So now I'm going to change to a different color, let's say red, and say I have a rising edge. Okay? The clock pin is going from 0 to 1. So this 0 is going to a 1. How is that going to change the circuit? Okay, so that's what we will analyze next. So we can see how this 1, okay, this 0 going to 1, this is now 1, and it goes here. So this is now a 1. Would that change anything? From the perspective of the SR latch S. Nope, doesn't change a single thing from the perspective of SR latch S, because when both inputs of an SR latch are 1s, the SR latch is simply going like, okay, I'll remember what you told me to remember. It's all good. It will just maintain the output. Okay, what else is it going to change? Well, we know the clock pin also goes to one of the inputs of N1. So that one, so N1 is no longer, we can no longer determine the output of N1 just from that. Okay, so we'll put a 1 over here. So now the output of N1 depends on the other two inputs of the same NAND gate. So now we have to track that down. Okay, so we track down this input here, and it is coming from not Q of SR latch S, and that's not going to change because we know SR latch S is told to maintain its current state. Okay, so we know that one's going to be a 1. What about the third one? So now we track down the third one. Okay. It goes to N1, and it goes to the output of N2. So now we have to track down, okay, what about N2? What is it going to do? Well, N2 is not going to do a single thing because D is 0, right? And that goes to one of the input pins of N2. N2 is going to output a 1 regardless of what the other input pin is going to say. So now we can go to, what was I tracking down again? This pin here. So now we know all 3 pins are going to be 1s. Yes? Okay, if we know all 3 pins are going to be 1s, then we know the output is going to change to a 0. It was a 1 before, but now it is guaranteed a 0. Okay? So we say, nope, this is going to be a 0 now. If that is a 0, it's going to not R of SR latch C, right? So that means we are asserting the reset pin of SR latch C because both S and R are active low signals, okay? So that means from the perspective of SR latch C, it's going to change its output. It's going to change its output because this is now going to be a 0. So the output is going to be a 0 as a result. Is that okay? So now you say, okay, so let's say the circuitry has this particular state at this point. What happens when I change the data pin from 0 to 1? How do I know this entire circuit is not going to change the output pin Q from a 0 to 1 just because I changed the data pin from 0 to 1? So I'm going to leave that as an exercise for you guys to do, but it's the same approach, okay? You start with the change of the pin over here, and then you look at where that pin is going, and then you look at the components of the system and go like, okay, how is that going to change the state of this particular component, okay? Can it determine the actual output of this component, okay? And you basically just go through the same kind of analysis, propagate a change to everything, and then you look at the actual output and say, well, what is going to happen to the output? Is something going to is something going to happen to output pin Q or not? So I'm going to leave that analysis to you now that I have kind of shown you how to approach it. So as I said, you probably want to print out several versions of this circuitry and then just use a colored pen or use a tablet or use whatever means that is easy for you to keep track of all the changes of the wires. Is that okay? Now, obviously, one other way to do this is to run this in LogicSim. But that means you don't have to think. Which means, you will get the right result, but you may not be able to explain why it is the way it is. Does that make sense? So I would encourage you to try to do this manually first, just like what I'm doing here. And once you have your theory of what's going to happen when we have a transition of 0 to 1 with a data pin in this particular state, run it in the simulator then to make sure that your understanding or your prediction is exactly what LogicSim is going to give you. Is that okay? So you can look at this as your ungraded assignment, okay? Because it is the kind of exercise that you need to do in order to fully understand how these circuitries work. Are we doing okay so far with this? Okay? So the way I did it, okay, when I wrote the notes, when I did this, I did not even bother to use a graphical way to do it. I just kind of maintained the state and use a written form to do it. So in other words, the analysis is already done, okay? It is already here, just in a text form and not in a graphical form that I just illustrated a little bit earlier. Are we doing okay so far with this part? Okay? Yes? Okay? So section 5.3 is about your clock steady state insensitivity, which means if I'm not having a transition, if the clock pin is a 1 or it is a 0, how come the data pin does not do a single thing to the output Q of the entire circuit? Okay, so that's basically what this analysis is about. But it's the same thing, okay? We just start with whatever pin is getting changed, and then we follow we propagate the change from that point on, and then we observe what is going to happen to the rest of the circuitry. Is that okay? Okay, all right. So now we have another circuitry here. You go like, well, isn't this a little bit redundant? Because it is both clocked and gated. You can look at gated as level sensitive, okay? So this one is both. It is both clocked or edge sensitive and also level sensitive, which is also called gated, okay? So what is happening here? Well, what this means is if enable is a 0, I don't care about anything else, okay? It can have a transition at the clock, the data pin can keep changing, nothing is going to happen, okay? If the enable pin is a 1, then we have to be careful. If the enable pin is a 1, then whenever the clock goes from 0 to 1, that is the moment that the data pin state is going to be copied to the Q of the output of the entire circuit. Yes, go ahead.
Is clocked always like rising edge, or is there like a high to low?
So in the circuitry that we are analyzing, we are only going to use rising edge as a default of the edge that is the circuitry is sensitive to. But that's a very good question, okay? What about circuitries that are sensitive both ways, right? You're sensitive to both the rising edge and the falling edge. That's what double DDR is about, okay? So when you think about DDR, I mean, you guys are have heard of that term, right? DDR2, DDR3, DDR4, DDR5 now, I think. Is that right? I think so. I think some of the newer processors use a DDR5 memory. So what is DDR? What does it mean? What does it do? Why do we have DDR? It's double data rate, but it's not doubling anymore. It's actually a little bit faster than doubling. But why do we need DDR? I mean, why don't we use memory before DDR was available? What does it do? How does it help? What do you think? So the answer to that question will be answered in about 2 lectures. Okay, so when we get to the explanation of how memory works, remind me to talk about DDR. Okay, so but right now we'll just say that these circuitries are only sensitive to one edge, particularly rising edge. Okay. Well, what is the quickest and easiest change to make this circuitry so that it is sensitive to a falling edge instead of rising edge? A NOT gate, exactly. So you just negate the clock pin, now it becomes falling edge sensitive. It's as easy as that. Okay, so we are not really too concerned or hung up on, oh, why is it always rising edge? Why not falling edge? Well, because to make it falling edge sensitive, you just need a NOT gate. After the input pin of the clock pin. For the rest of the circuitry, just take the negated version of the clock. That's all. So are we good so far? Okay, so if you were to build this actual circuitry, you can test it out. Okay, in other words, you can test it with En being a 0. Okay, then you can play with the other 2 pins all day long and nothing is going to happen to this particular Q output pin. Okay, the only time you can change that Q output pin is En is a 1, clock is having a transition from 0 to 1. And at that moment, whatever the data pin has will be copied to the Q output pin of the entire circuit. But you can see this one is kind of more complex because it has got 2 AND gates. So these are AND gates, they're not NAND gates. And it has got 3 SR latches instead of just 2. So the complexity is increased a little bit, but it does a little bit more. If you want an analogy of what this is, it is a digital camera. I think I talked about that already. Okay, this is like a digital camera where you have an on-off switch. So the on-off switch is the En, and then the shutter release button is your clock. Is that okay? All right. So we are going to move on to the next one, which is a resettable. Okay? So if you read the section header, oh, the section header doesn't say that. What is the full name? I did not even write down the full name. Okay. So this is a clocked, gated, and resettable D flip-flop. What is the change? The change is right here. I added a reset pin. So the rest of the circuitry is pretty much the same as before. So now the question is, what does reset do? Okay? So you have to track down reset, and the only thing that we are doing here is the reset pin and 2 additional gates, 1 OR and 1 AND, is inserted before the final SR latch. Well, what is that going to do? Well, let's go ahead and take a look at what happens when the reset pin is a 0. Okay, what is that going to do? So now this pin is a 0. The 0 goes all the way here. It feeds into A3. If this is a 0 and A3 is an AND gate, what is going to happen to the output? Guaranteed a 0. That 0 goes into R, which means the output pin Q is going to reset to a 0. Okay, so this reset is also active low. I should have put a slash or an exclamation point before the reset because it is also an active low signal. Well, what about the other one? What about the OR gate? Well, the 0 is going to be negated before the OR, and we have a 1 into the OR gate. So if you have one input of an OR being a 1, the output of the OR is guaranteed to be a 1. Well, that 1 is going to the set input of the SR latch, which means we are not going to do anything. We're not going to set the SR latch, the final stage SR latch. Is that okay? What if the reset pin is a 1? Well, if the reset pin is a 1, okay, once again, we follow the wire, it's not going to do anything to A3 because you simply have guaranteed one input of an AND gate to be a 1. Well, 1 and whatever is just whatever. So that means the AND gate becomes transparent. It's as if it is not there. Okay? What about the OR gate? Well, the 1 is negated before it feeds into the OR gate, so that means by the time it feeds into the OR gate, it is now a 0. False or whatever is whatever. So that means it is also as if it is not there from the perspective of the OR gate. So that means if the reset pin is a 1, it is as if we just had the circuit right before this. Okay? It is just a regular, gated and clocked D flip-flop. Is that okay? Well, who's in charge of the reset pin? Because it seems like the reset pin has priority over everybody else. So the question is, who's in charge of asserting the reset pin? What do you think? And why do we have this reset pin? Why is it important? Okay, the user, well, usually the user has a way to set the reset pin or to assert the reset pin. But what else?
Well, I think whatever powering on or off the circuit, the more quickly powering on, it ensures it has a state.
Exactly. So when you first power up a computer or anything that has circuitries like this, the SR latch is going to go like, I have no idea what my current state really is supposed to be. Okay? So that means your computer has an unknown state to begin with, because it all depends on a lot of different things. Okay, like did you turn on the microwave while your computer is being turned on? How close are you to the computer? What is the ambient temperature? And a whole bunch of other things, right? So you don't want your computer to only properly start up when the room temperature is exactly 68 degrees and you are 5 meters away from the computer and no one is using the microwave, right? Okay? So when you first power up the computer, there's a chip on most circuit boards called a supervisor chip. So the supervisor chip has a special feature. It can detect power on transition. So it monitors the actual power in or the VCC or the regulated voltage. When it sees that voltage dropping below a threshold, it will assert the reset pin. Okay? It will keep it low for a period of time. So even after your VCC or the regulated voltage gets up to a healthy point, the supervisor chip will maintain the reset pin for a little bit longer. When I say a little bit longer, it is measured in milliseconds, which to the computer is a long time. Okay? So the idea of the supervisor chip is to make sure that power is stable for a reasonable amount of time before it says, okay, everybody, now you can move on and do stuff. But everything is reset to 0 right at that moment. Is that okay? All right? Okay, so that happens when you power up something. What about your Android phone? When was the last time you have to disassemble your Android phone, take the battery out so that you can turn it off or reset it? I have done it once or twice for the first generation of Android devices, but you don't have to do that anymore, right? So how do you reset your phone when it hangs up? I mean, it does happen once in a while. Throw it against the wall really, really fast, right? So what do? You hold down some buttons, right? So what happens over there is when you hold down those buttons, it actually has a hardware circuitry to hook up to the supervisor chip. So when something times out, it will cause the reset to happen too. Now, you might also notice that sometimes your Android device or your PC or other devices will reset by itself. Okay? If you try to run an app or if the upgrade fails or something, and the computer doesn't work, okay, it hangs up. After maybe 10, 20 seconds, it will reset itself. How does that happen? The supervisor chip. So the supervisor chip usually also has a second mechanism called a watchdog timer. So the watchdog timer, which is, I guess, a semi-technical term, is the same thing as a dead man switch. Okay? Does anyone know what is a dead man switch?
Yes.
Okay, and what is it?
Switch used for IDs or stuff like that, or when you die or release it, it goes off.
So you need to be alive to make sure that it does not go off, right? So a dead man switch combined with a timer is what we call a watchdog timer. Okay, so the watchdog timer is a device where it has an internal timer. Okay, so the time period may be set to 5 seconds or 10 seconds or 20 seconds. Okay, so every 20 seconds or so, it needs to be hit by software. So that means the operating system, Android, iOS, Windows, Linux, whatever, okay, needs to set up a timer to say, okay, every 5 seconds, every 2 seconds, to be safe, I'm going to hit the watchdog. And every time you hit the watchdog, the timer resets. Okay, so you have another 20 seconds before it expires. Does it make sense so far? Okay. So if your system is in a state that is so hung up that the operating system is completely locked up, no one is going to hit the watchdog anymore, right? If the watchdog is not hit, then the timer will expire. When the timer expires, then it's going to cause the reset automatically. Is that okay? So it's a really kind of cool device, because if it means that if your device, for whatever reason, hangs up, it can reset itself. So all of that stuff is a little bit beyond the scope of this class, but it is a major component of computer architecture. You will see that again when you get employed. All right. So this is the last part, okay? What is a multi-bit register? So when you look at the circuitry, you go like, hey, we recognize some of this stuff, okay? This thing here is a resettable, clocked, and level-sensitive D flip-flop. So each one is like that, okay? But how do we hook up the entire thing? When you look at this circuitry, let me zoom out just a little bit so that we can see the entire thing. You can see that, well, even though there are a lot of wires flying around, some wires are shared by a lot of devices. Okay, so let's look at the wires that are shared. So when you look at clock, okay, clock is clocked here, 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 and here. So all of these D flip-flops connect to the same clock. They're sensitive to the same edge. What about enable? Okay. Same thing. So when you track down enable, it is multi-dropped into every single D flip-flop. What about reset? Okay, it's down here. No, reset is where? Down there somewhere. It's the same thing. Okay, if you track down this reset, it is also multi-dropped into every single D flip-flop. So those wires are connected to every single D flip-flop for control purposes. The only wire that is unique to each D flip-flop is a data bit coming in from the multi-bit pin called D, which is data. Is that okay? So each D flip-flop is responsible to store an individual bit in a byte in this case. Is that okay? So when you look at the output of the D flip-flops, same thing. Each one is responsible for an individual bit of the output pin that we call Q. So Q and D are now multi-bit pins instead of the individual pins or the individual bit pins from before. But this is how we can remember a byte. So do we have any questions about this picture? And this circuitry here is also known as a register. Yep, go ahead. Yes, because it is a multi-drop. So when you, oops, hold on a second. Yep, doesn't want to scroll down anymore. There we go. So you can see the reset pin is the same. It's a multi-drop. It drops here, drops here, drops here, drops here, drops here. So when the reset pin is asserted, it will reset the entire thing to just 8 bits of zeros. Are we good so far? Okay, so what you're looking at here is called a register. Okay, and a register is one of the most elemental components inside a processor. Are we doing okay so far with this picture? Yep, go ahead.
Are all registers clocked and gated? Or are there some just clocked and some just gated, or is it like?
Inside the processor, they are all clocked and gated. There are reasons for that, okay? So it's a little bit premature, but I want to show you why they are like that. So let me show you that picture. So let's go back to Logisim, and this time we're going to load the processor. Okay, so we'll go to here, and I think this is the correct. Okay. This is going to be your best friend from here on until the end of the semester. So each one of these, okay, so let me show you what a register looks like from this perspective. This is a register, this is a register, and inside here, there are 4 registers. So the processor is basically a whole bunch of registers, and they're interconnected by some other components, okay? The reason why they have both the clock and also the enable is because the clock of almost every single register are connected to the system clock. So there's a system clock that clocks everything, okay? So that one, on 101010 connects to every single register in the entire system. So now the question is, when we see a rising edge, who is going to change? Not all of them, only some of them need to change. So that's why we have the enable pin or the gating mechanism to basically say, okay, I know all of you are getting the same beat, okay, but you don't need to change, you don't need to change, but I do need you to change. So it's a control mechanism of specifying which register needs to update when we have a rising clock. Because the rising clock and the falling edges will keep going, and it's universal to all registers. Is that kind of okay so far? Yeah. Okay. Mm-hmm.
What's the difference between that and just having the enable?
If you just have the enable, then you don't have timing mechanism. Okay? So think about the ALU. Okay, the ALU is going to do some calculations, right? And I want to store the result of the calculation back into another register. So how do you know when is a good time to update the other register, right? So because sometimes we want to supply a value to calculate and store the result of the operation into the same register. So now, without the clocking mechanism, without the synchronization, which is what the clock is about, then we cannot determine when is a good time to update. So the clock mechanism is for controlling the timing of an update, whereas the enable is for specifying who needs to update. So they control 2 entirely different aspects of an update of a register. Okay, so that's a very good question. Go ahead.
So is the system clock like the same thing on a processor, like the same thing as like the clock speed, like 3 gigahertz, 4 gigahertz?
Not entirely the same. So your system clock, there's a clock going into the processor, but that clock cannot go at 4 gigahertz, okay, or 3 gigahertz, or even 2 gigahertz, because to send a clock over a wire about this long, and the clock frequency is 2-3 gigahertz, it's not doable. Okay, you simply cannot distribute a clock clocking at that kind of frequency over this kind of distance. Why? Well, because of physics. Because we have capacitance, we got inductance, and we got, to a certain extent, resistance. All of those things will degrade a signal. And when you're clocking at that frequency, the slightest degradation of the signal is going to cause the clock signal not to be a smooth, not to be a sharp edge anymore. It's going to look like a shark fin, and that means it's difficult to tell when it is transitioning between a 0 and a 1 because it's not a very sharp line anymore. So that's why we cannot distribute a system clock at a gigahertz frequency. So what happens is the system clock is usually running at sub-gigahertz. So we maybe talk about 800 megahertz or something along that line. That frequency goes into the processor, and then in the processor is a circuitry that we call a frequency multiplier. The frequency multiplier will take this input clock signal and be able to multiply it by a certain factor to become the actual internal CPU clock signal. Now that's okay because the clock die, the CPU processor die is only about this big, right? So it's okay to distribute a multi-gigahertz clock within the processor itself, but not when it's outside. So is that kind of explaining a little bit of, okay. So that's why when you look at your DDR memory, the clock of your DDR memory is what, up to 1.2 gigahertz now? Yes, no? You guys don't build your computers anymore? Yeah, this is kind of interesting because not only are we not building our own computers anymore, even for laptop computers, you can't buy memory chips anymore. Because on a lot of the less expensive computers, or the ones that are super slim, the memory is soldered onto the motherboard. There are no sockets, okay? So unless you say, I know how to desolder chips and solder new chips in, there's no way to expand the memory anymore. So we still doing okay so far? Okay. Anyway, so this is the processor. But since we are here, okay, we're going to talk about some components because now this is the pine forest. Okay, we get to see how everything are connected. So we got two kind of interesting pieces here. This piece here, just looking at the time, we are running out of time. This is our memory. Okay, this is RAM, and then we also have ROM down here. So since we are running out of time, let me do one more thing before I dismiss the lecture, which is to go back to my notes here and find out what the next lab is about, because I want to see whether we have enough to start the next lab. And we don't. Okay, so I'm gonna let you guys go today, without a new lab, simply because I have not covered enough material to start the next lab.